going back and forth because the graphical of this is actually super helpful. So improper integrals, a big help to topic actually. They are improper if, so we're going to be integrating now after limits and derivatives of the last section, if they have limits of infinity. So for example, if you're going from 0 up to infinity, and basically remember what a definite integral means. It means you're finding the area beneath the curve and the x-axis. And when you head out to infinity, that does seem kind of improper. Like, how can I get a finite amount of area when I'm heading out to infinity? That seems kind of weird, correct? And some you actually don't get a finite number. You actually will say they diverge and you can't get an answer. But that would be like the structure. Another one would be like if you went from negative infinity to 5 or something. They're easy to spot in this first type because you'll actually see an infinity symbol on the integral. You could even have it on both so that you're heading to both infinities under the curve of f of x dx. And again, f of x is just some function under which you're integrating. So that's the first scenario that's called, and that's what we're going to work with today. So what is today, Wednesday? I'm going to put a Wednesday right there. We're going to stick with the first type today. The other type, though, I'll just mention, but we won't talk about it till tomorrow. The other type of improper integral is, again, when you have, I'm going to show you the issue of this guy. Suppose my function was the volcano graph, 1 over x squared. Suppose I was up in the first quadrant, and I was trying to integrate from 1 all the way on out to infinity, which means technically I'm trying to find this area in here. But I'm heading out forever and ever and ever and ever, so doesn't your gut kind of tell you it have an infinite amount of area? It actually doesn't. So some end up being finite, like you can actually say the answer is 12. And some it's like, no, the diverges, I can't grab an answer. So it's not about it going to infinity, it's kind of about how quickly it starts to collapse towards 0. It's sort of what it's about. The other issue is when you have what we call a discontinuity, an infinite one. So what that means is a vertical asymptote. So you're trying to integrate, it didn't spell that very well. You're trying to integrate, and there's an asymptote either on one end or the other or on the way. These are hard to spot. These in multiple choice kids will they'll forget to look for it and they'll integrate as normal, and sometimes you get a wrong answer. Let me show you what I mean by that. If I make a function that's x minus 3, I'm just going to make a fake one right here. Where is there an asymptote on it? 3. So if I'm integrating from 3 up to any number, 5, I can't deal with the 3 because there's an asymptote there. Does that make sense? So you're actually heading up forever. You can't actually get there. That's when it's on a limit of integration. Or if I was doing the same one, just for shits and giggles right here, if I was going to 2 to 5, you see what the issue for that one would be. I'm trying to find the area under the curve, but along the way, what do I hit? A vertical asymptote. So it can cause issues, and I have to teach you how to decide whether there actually is a finite amount or whether we diverge. So we're going to have 2 different types of answers with these. We're going to say they converge, which means actually an answer. Like the answer's 5, and we'd say the integral converges to 5. Doesn't technically ever get there, but it gets to 4.99999 whatever. It's 5. Does that make sense? Or it diverges. Like you keep going and you just can't grab an answer. It just keeps getting like bigger and bigger and bigger, or smaller and smaller and smaller, in which case we say we diverge. So there's 2 possible answers. Okay, so 2 answers. Diverge, which means you integrate and you get an infinite amount, basically. Or converge, which means you integrate and you get a number. So if you know how to integrate, life is good. And the integration in these isn't too bad. It's usually just pretty easy. Power rule, a U sub. Sometimes there's a by parts in there, but you're not going to be like doing partial fraction decomposition in this skill. So if you can integrate basic ones, you're going to be good with that part. It's the notation. So first of all, I'm going to show you what happens with this guy right over here. Alright, if I go from 1 to infinity, under the graph of 1 over x to the power, and if I keep changing the power, there's a pattern, and I'm going to show you what happens on decimals. Are you ready? So, I actually have that first one in there. I can do this, and we're going to do which one are we going to do? The x cubed one we're going to do by hand. But first we're just going to investigate, take a little observation tour here in decimals. So do you see how I graphed 1 over x squared? Do we see it? Yep, and I'm integrating from 1, so right about here, out to infinity. I'm trying to find that area. By the way, did this approach 0 pretty fast? It did. So my gut tells me it's going to converge. Like it actually is collapsing so fast, my guess is I'm going to get a number. Decimals doesn't allow me to put infinity, but it'll allow me to put pretty big stuff. So watch. 9, 99, 999. Do you see what that's approaching? I'm going to go back 1. What does it look like we're approaching? 1, and it is. Okay, so right equals 1 on that first one. 1 over x squared. If I did it with calculus, we're going to get a 1. We would say that integral converges to 1. I'm going to go back to 9, and now I'm going to take the graph of 1 over x cubed. And I'm going to talk about gut instincts. Didn't that even go faster? Do you get why it went down faster? The denominator's getting bigger, correct? Right? So if you're under something that converges, don't you think it'll converge too? Kind of like a car. Like if something's converging this way to crash into the wall, and aren't you going to crash as well? Right? So my gut tells me this will converge to something less than 1. It's going down faster. So there's a lot of common sense in here too. All right, so watch me bump that up. I'm at 0.88. Oops, I forgot to change this to cubing. I'm like, why is it staying the same? All right, now take a look at what I've got. What does it appear to converge to? If I had a gun to your head, you'd say, it's going to go to what? A half. Go ahead and write a half by the 1 over x cubed. It converged to something less, which makes sense because it's riding under it. Agreed? Does that make sense? What does your gut tell you is going to happen when I put a 4 right here? Wow, it went down even faster. So my guess it'll converge as well, correct? But to something what? Lower. Okay? And I want you to write these as a fraction. What fraction is 0.333333333? 1/3. Okay. Are you seeing a pattern? Look at your numbers. 1 over x squared went to 1. 1 over x cubed went to a half. 1 over x to the 4th went to a 3rd. What do you think 1 over x to the 5th is going to go to? It will. And I could prove it, and I have in the past, but I took that out of the notes because it muddles the issue. It's like a 15-minute long proof. So I just wanted you to see it. But you can now see how this says 0.25, correct? So those are all converging. If I went to 1 over x to the 7th, guess what it's going to converge to? 1/6. Okay? Now watch when I go the other direction. Are you ready? So I started with 1 over x to the 2nd. Now I'm going to go to the 1st. So it will ride, its graph will ride. Why isn't it graphing that? Oh, that's kind of dumb. All right, there. So now this guy is riding higher than 1 over x squared was, correct? It's above it. Maybe it converges. I don't know. I'm going to take this 5 out. Are you guys listening over there or something funny? All right. So I'm going to go here and take a look. It says 16. Do you see the 16.11? Watch me add another 9. Now it says 18. Are you 100% sure what it is? No. And if I put another 9, it says 21-ish. What's happening? It's growing, not shrinking, correct? And not in a consistent manner. I could keep putting 9s in, and it's just going to keep growing, and I'm going to be like, I don't know. If you had a gun to my head, I'm going to guess 24. No, now my calculator wigged out on me. All right? So this guy is not settling. As I make that top go to infinity, it's not getting smaller and smaller and approaching like a 3rd or a 4th. It's getting bigger and bigger and bigger, correct? What do you think we say it does? It diverges. Okay? So by 1 over x, I want you to write diverges. Now watch me just change this guy right here to something with a lower power. So I did 2, 3, 4, 5, 6, converged, 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 converged to smaller, smaller, smaller. Should make sense, right?
At 1 over x, I diverged. I'm going to change that to a square root. And just kind of watch up here. It's pretty not stressful today just because the homework isn't due for a while. It's going to ride above. I'm going to go put 1 over x back on there just so you can see it because it's actually important for our series chapter as well. Do you see how the white one, the root x, I mean the orange one, the root x is above the 1 over x? Do you see it? And if the 1 over x diverged and this one's above it, won't it diverge as well? Doesn't that make sense? And anything, I could change this to a cubed root, and it's going to even go above it and above it and above it. So we're going to have a little rule, and that's what I kind of took out of the notes was the proof of all that. I just wanted to show you. So back to your notes here. I'm going to show you what happens with these. This guy, we got a 1 over 1, or just a 1. This one, we got a 1 over 2. This one, we got converged to 1/3. This one, we converged to 1/4. What do you think if you Googled it or looked in a math book? It would say the integral of 1 over x to the p from 1 to infinity converges to p minus 1. Yeah, 1 over p minus 1. I could write a proof for it. I don't want to right now. Okay? It's a fact. What did we say happened once we went and made it 1 over x to the first? Diverged. And then what happened here? Diverged. And what would happen if it was a cubed root, a fourth root, a fifth root? Diverged, diverged, diverged. I want you to circle this one, and actually not for this chapter, but in another one, we're going to call 1 over x the fence for divergence. Everything above it diverges, everything below it converges. Okay, we're going to call that one the fence. So here's my conjecture. A conjecture is something I see happening, but I don't want to prove it. My conjecture is this, that if I go from 1 to infinity of 1 over x to a power dx, my answer will be one of two things. It converges to 1 over p minus 1. Provided, this is what you'd see in a textbook. What had to happen for it to converge? Do you remember where I started? Greater than 1, thank you. I thought you guys might say greater than 2, but actually at 1.2 will do it as well. So greater than 1. And we diverge when p is what? Less than or equal to. 1 is the fence for divergence. Now that's pretty easy to understand. It's sometimes helpful, but not usually, and usually not. Every once in a while for an AP multiple choice question, that's nice to know. Because here's an example. Sometimes it'll go like this. From 1 to infinity, and it would be 1 over x to the pi times k. Go ahead and write that. And it'll say, for what values of x, I lied, k, does that converge? And you would say, well, I need that exponent to be greater than what? 1. So what does k have to be greater than? 1 over pi. Every once in a while, knowing what I just showed you is helpful for that. But my main reason for showing it to you, though, is the idea of some of them converge if they go there fast enough. If you're below a convergent, you have to converge. Some don't go fast enough, and we call them divergent. And if you're above a divergent, you diverge. What I just said is the most important thing. Did that make sense? Are we good with that? All right. So now I have to teach you how to do it without, like we were just doing it on decimals and just kind of guessing because we saw 0.25 that it was a fourth. But how do I get to that a fourth? On the bottom it says, we're going to have to use some limits. Infinity is not a number. So we have our fundamental theorem of calculus that says we do an antiderivative. We plug the top number in minus what we get when we plug the bottom number in. But that infinity is not a number. So that's why we have to have proper notation here. So let's look at these two. I know the answers already. I purposely redid the notes. You're like, I know what I should get. She just did this. We got 1 over 3. That's what I'm going to get. On this one, what did we get with 1 over x? Diverges. Okay? We saw it. We did it on investigation, but that's really not a fact until I can show it. Alright, so this is how I'm going to go really slowly because it's the notation that's going to get you. The concept's actually fairly, I think, easy to understand. We're going to integrate from 1, but we can't get to infinity. We can't plug infinity in. It's not a number. It could be
I could be farther along in one problem than I am in another. So you put a placeholder in for it. I always choose B. You might get a professor though who chooses A. T is pretty common, but they look like pluses, so I don't like them. So I always use B. I still integrate the exact same problem. And then I take a limit. What do you think I'm going to have B approach? Infinity. So it's going to become a limit problem. And this is where kids lose their notation point, because I'll show you when we do the FRQs on the scoring rubric, it's going to say student uses proper limit notation. So if you just do it and get 1/3, you won't get the notation point. All right? So here's what you do. You block out the fact that it's a limit for now. You're just going to go integrate like you've always integrated. You're going to take the antiderivative of x to the -4th, or whatever's in there. But it's usually a power function or a nice by parts or something pretty straight. U sub maybe. What's the antiderivative of x to the -4th? X to the what? -3rd over what? -3. Okay? Do it off to the side. Alright? And what I'm going to do is head on this. Oh, actually, I'm going to go in here. I'm writing really big. I'm going to make it a little smaller. I'm going to take a limit as b approaches infinity. I am going to have x to, you don't want negative exponents in these, by the way, because you want to see when things go to 0. So go ahead and put that at the bottom. It looks like I would have a 1 over -3 x cubed. Good so far? Right now? Pretty straightforward. I'm just integrating. You still have the limits. Once you're done integrating, your limits go over here. I'm going from 1 to b. So nothing's changed so far, except now all of a sudden I have this limit in front. What goes in first, the b or the 1? Okay, I'm going to put that in first. I still am. The only thing I'm doing differently, so I put the b in, and then what do? Fundamental theorem of calculus. After the b goes in, what goes in? The 1, and what do I do with them? Subtract them. Exactly, Alexis. So I have minus a -1/3 once I put that in. So it's plus 1/3. That has not changed. The only difference is you got to keep putting this limit out front. Once you're done, so here's how you're done. You set up your limit. You actually integrate it. You plug the top and the bottom in and you subtracted them. Now you send b to infinity. What happens to this? This goes to 0. What's my answer? 1/3. What did decimals kind of seem to look like it was? What did it look like it was when we did it? 1/3. Now you can kind of see why they end up being p minus 1. Just watch. If this had been a 5, this would have been a 5. This would have been a 4 and a 4, right? You see the difference? So that's why it goes down 1. That would have been a 4 and a 4 and a 4, and you would have had a 4. That would have been the only difference. Does that make sense? Watch the diverge one. Are you ready? So I want you to actually you write the integral down. Rewrite your integral. If you don't, you lose a point. So it's not actually catastrophic if you can't do it with limits, but you won't get higher than a 7 out of 9. Which is still really good, but you need to know the notation if you want to be able to nail this on an FRQ. We know it's going to diverge, I showed you, right? So you're going to rewrite, keeping the constant there. We like 1. 1's always been a 1. What am I going to put on the top? A b or a whatever, your variable of choice. Do a b though, it's easier for me to read it. What am I going to put in front right now though? It's a limit. As what happens? There we go, b approaches infinity. So there's my rewrite. I'm using proper limit notation. The next thing, I bracket this off. That's just a rude thing though, because I like to the limit bugs me. I'm like, I just want to integrate it. So just go integrate it. What's the antiderivative of 1 over x? Nope. Alright. Antiderivative. Thank you. What'd you say, Alexa? It's hard because we've had limits, derivatives, and integrals in every lesson before this. So we've got limits running. We're integrating now. Yesterday we had derivatives and L'Hopital's in what? Right? It's the natural log of what? Absolute value of x. It's integrated. So your limits now go on the right. I think I have two of you who sometimes still put them over here after you integrate. Don't do that. You'll lose notation points. Right, so there's that guy, right? If you continue, you're going to lose notational fluency. Because what's got to go next still? The limit, yeah. You're still taking the limit. So until b goes in, your limit stays. B's going to go in right now. It'll be a natural log of b, top boundary, minus natural log of the bottom boundary. I'm still sending b on out to forever. How are we doing, Jacob? Good? And what's the natural log of 1? 0. What will the natural log of b approach as b approaches infinity? Infinity. That's why we say it diverges. How are we doing so far? Oh, terrible at drawing infinity symbols. You know what I'm terrible at writing? Cosecant x. I don't know, the muscle memory of writing like the C and the S and then the C, I can't do it. Alright. It's weird.
I can't draw brackets.
Yeah, I had it in geometry today where we're doing a triangle sum theorem. You can see it on the back that the angles in a triangle add up to 180. And the kid's like, I can't draw a triangle. I'm like, oh, sweet. You've got so many more issues. You just can't draw a triangle. I'm like, oh my god. Alright. Anyway, be very careful on that last thing I put on that page. I said this is sometimes helpful, but usually not ever usually helpful. Here's the problem. That 1 over p minus 1 convergence and divergence stuff only works when you go from 1 to infinity. And you're going to be tempted to do it every time you see something with a power in there. So you do need to crank them out by hand unless you're 1,000% sure you're going from what to infinity? 1 to infinity of 1 over x to the p. Then if you remember the shortcut, feel free to use it. Otherwise, that's not a 1, and so we need to start. I want you guys to take that guy and run through as far as you can get. You're going to decide if it converges, if so, to what? If it diverges, it means you got an infinity or a negative infinity, but you still need to write diverges. Okay? So there's some seemingly infinite amount of area that may converge to something that it will never pass. Have to integrate properly, though. Thank you, Grant, for getting there caught up. Take a look at my work, so you can see it. I changed to a power, added 1 to it, divided by it. Limits go now on the outside. I changed my 1/2 power to a root because I like it like that, but it's not wrong. I actually think I dealt math on Friday to leave it as 1/2. It doesn't matter, but. And then I plugged the b in, and then the 3 in, and I made a mistake. There we go. Yeah, I caught it, right? Now I need to know what the answer to that is. As b goes to infinity, where does that thing go? Twice infinity minus a minute amount, correct? What do you think it goes to? Infinity. Infinity plus or minus anything, including its, I forgot to put that. Infinity plus or minus any constant, what are you going to get? Infinity. Infinity minus a gazillion is still infinity. Make sense? What's infinity plus infinity? Infinity. Don't say two infinities, right? It's not combining my terms. We're really heading there, right? How about infinity minus infinity? Indeterminate form. If that pops up, which it actually is going to, I don't think today, you're going to not say it's zero. You're going to be tempted to. You're going to be tempted to write zero and write converges to zero. But that needs a little bit more. I don't think that's today, though. Anyway, we would call this an improper interval that does what? Diverges. All right, so now I'm going to just keep the same skill. We're just going to start messing with the integrand a little bit. We're going to move away from x to a power. So the next one up. Oh, improper integral. I see it. The infinity ones are easy to spot. Is this something easy to integrate, though? Yes. Here's the graph of it, by the way. E to the negative x looks like e to the x, but it goes in reverse. I'm being asked to find how much area accumulates as I head on out to infinity. It seems like you want to write diverge. It might, but it might not. Right? I actually don't know. I haven't done it. So we have to go do it. So let's see if we've got the process down. Is this better than yesterday? Same sort of? Yeah. All right. So I'm going to head from 1 up to where? B, e to the negative x, dx. I rewrite it like that first. I always kind of write them. This is the one case where I like to write my work in reverse. I deal with the integral, then I tack on the limit. Integral, then the limit. Write it out, then do the limit. So what's the antiderivative of e to the negative x? You need to know it. Negative e to the negative x, correct? But I said I want right negative exponents. So yes, it's negative e to the negative x. That's kind of hard to work with. I'm going to write it as negative 1 over e to the x. I would always do that. Either make it a two-stepper and write it with a negative x first and go, I'm going to put that underneath. All right? I am now out of the integral, going from 1 to b. I'm still taking the limit. So that's kind of your workflow. Who goes in first? B. Okay? So I'm going to erase part of my graph here. I've got my limit. I've got b heading on out forever. Negative 1 over e to the b. And then I have a minus. Now be careful. Minus of what? Negative 1 over e. So what am I going to put? Plus 1 over e. So I'm going to be really careful. Now as b goes to infinity, what does this thing go to? 0. Thank you. That's gone. So what is the answer to this? This actually converges to what? 1 over e. If I went on to decimals and I set that top limit to 999,999 and had to do a number, that decimal would be 1 over e. Okay? Let's try the next one. We're getting close to the end here, actually. The next one. Here we go. I'm going to go from 0 up to b. X, e to the negative x dx. I'm going to take my limit. I'm going to send b on out forever. Now I'm done with proper notation for now. I have to integrate it. Now you have to know how to integrate x, e to the negative x. Think about that. You can't integrate it, you're not stuck. How do you integrate that sucker? But that's a bipartser. What triggered it for you, Carissa? The x and the e to the x. I do that off to the side. Just throw it over here. You got a bipartser. Just to repeat, how did she recognize it was bipartser? No. They're functions that are what? I call them incompatible. That's a really good trigger. Who's your U choice? Who's your U choice? Yep, algebraic. Your dv is the e to the negative x. du is 1. And what's the antiderivative of e to the negative x? Negative e to the negative x. So I'm setting up my biparts here. Oops, sorry if you're watching this video. I can't write that negative x up there. I'm going to still do it down here, actually. It goes ub, here's my ub, minus the integral of, and now I have to multiply these two, so that's going to become a plus. You're really watching my signs. How are we doing so far? Are we good? What is it? Negative e to the negative x. Now, there's a couple things you can do with this to make it easier if you want to. But I'll let you decide. What do you want to do with that negative x e to the negative x minus e to the negative x? Move them. I think I will do that too. I like that. Negative x over e to the x minus 1 over e to the x. I like that. Good so far? Are you okay with what I wrote? If you like it? Sometimes some people say, well, factor this out. It really doesn't help much, so I'm not going to. I'm going to go back and put that in here. I just did the antiderivative. I did what Chris has said, kind of put those negatives in the bottom. Once you're done, we go up here. And once we're done, don't forget that we're sending e to infinity. Next up. Now what happens? It's a heavy lesson for a couple days. It's nice the next thing it's kind of fun and light, but this one's getting a little heavy. It is what it is. What do I do next? Put the what in? The b. Yep. So I'll go negative b, e to the b, minus 1 over e to the b. Still taking the limit. Alright? That part. Then, subtract. Erase my by parts. Minus what I get when I put in a 0. What do I get when I put in a 0 right here? What do I get when I put in a 0 here? So I'd have a 0 minus 1, correct? How are we doing so far? Now I'm going to go back and talk about what these are. Technically, this is negative infinity over infinity. Technically, if I was picky, I'd make you L'Hopital it. But what should you know it goes to? 0. Yeah, the derivative of that would be negative 1, e to the b, 0, e to the b. Like, the bottom's so heavy, right? But technically, you L'Hopital need it, but that's going to 0. What's this going to? 0. Lots of things go to 0 if you remember to put those exponents in the denominator. So what's the answer? Yeah, if I were to graph this and head on out to infinity, all that area that seems like it's going on forever actually never breaks the 1 barrier. Alright, we'd say it converges to 1. So we call that an improper integral that converges. We'll just do one more. Alright, and then we'll stop. It's actually the same one. Alright, I'm just changing now your integration techniques, and then I also put one here that's got like a double infinity on it, but it's actually easy to bypass if you listen. So let's go fast. Can I go a little faster now? Yeah. Alright, let's go. We're going to head from 0 to b of our integrand. So I'm under this. This is actually a traditional bell curve is what it looks like. If you were to graph it, it looks like that. But doesn't particularly matter. If you keep on going, you're going to lose your limit notation point, so we're going to send b on out to infinity. Next up, antiderivate. You ought to know how to do it. It's not going to be any super hard techniques. We just had easy by parts. Thank you. This is an easy, straight in your face arctan. Good. No, because if you don't see it, you're stuck right there, and you lose all the rest of the points. This is arctan. What would trigger arctan, Natalie? Like, why did you say arctan so quick? Plus, squarings, no roots, and it's arctan in its most beautiful form. I'm not going to make it be like arctan root 2x over 5 with it, but it's just arctan x. We're good. And we're going from 0 to b. We're still taking our limit as b approaches infinity. Good so far? Hanging in there, Owen? Yeah. Awesome. So now I'm going to still send b to infinity, but before I do, I have to put my b into my arctan and subtract off, and then this is where some pre-calculus misconceptions need to be fixed. I think some people don't know what it means to take arctan or arctan. You guys know what that means? Like when I say what's arctan infinity, do you know what the answer is? See, someone said that. Most of you are going, no. So arctan of something means the tangent of what is that? So I'm saying the tangent of what angle goes to infinity. So you have to think of the graph of tangent and think of where do you go to infinity? There it is. Okay, you're reversing the process. So you have to kind of know Your tangent graph goes like this from pre-calculus. And I am saying, and you might want to hear, we're never taught why of that. I think now might be a fine time since we don't have homework tonight. If I were to say, y equals arctan infinity, correct? How do you undo arctan? I would say tangent of y would have to equal infinity. So I'm looking for the angle that goes to infinity. What is it for tangent? You said it, John. What'd you say? Pi over 2. What if I said, what's arctan 1? That's actually really common. I'm asking the tangent of what angle? Is 1. You won't have really hard ones. The tangent of what angle is 0? Tangent of what angle is 0? 0. So what's the answer? Pi halves. Now watch me combat this one really quickly. Are you ready? Again, a little bit of algebra 2 / pre-calculus. You guys remember what even functions are? Yes, sort of. She sketched one in your head. Even functions actually reflect over the x-axis. So whatever happens over here, there's symmetry over there. They often do have even powers in them. But this is an even function. So if I know from 0 to infinity I got a nice pi over 2, what do you think is going to happen when I go from negative infinity to pi? Double it. Yeah, it's just twice what I get if I were to go from 0 to infinity. So you could go through the whole process again, and you could use 2 different limit notations, but it would waste time. So we're going to actually quit for now. I'm going to put a bar right here. I'm going to stop